Okay, so this is Mendel's first law. The problem statement goes into some basic details about probability, also tells you about what a probability tree diagram is, and then does some other stuff, like it gives you an example problem with some blue and red balls and the definition of an event. It's worth reading, I think, especially for this video, because I'm going to be using a probability tree diagram. The given is three positive integers, k, m, and n, representing a population containing k plus m plus n organisms, and k individuals are homozygous dominant, m are heterozygous, and n are homozygous recessive. They want you to return the probability that two randomly selected mating organisms will produce an individual possessing a dominant allele, thus displaying the dominant phenotype. And you can assume that any two organisms can mate. So I think a good way to start solving this problem and Rosalind problems in general is by seeing if you can replicate the sample output they give you using their sample data set. And usually with these sample data sets, they give you some pretty simple numbers that are like easy to run through your code, I'm guessing, so it's just easier to troubleshoot. So let's actually start by thinking about what they're asking us to solve. So the part that I got stuck on actually is like figuring out exactly how to answer their question, because I didn't really understand mathematically how to represent their question. So I thought about it for a bit and realized it makes more sense when you kind of reword the question. So let me try to reword what they state in their return statement. So they ask this right here, but let me reword that as asking, what is the probability that A, two organisms mate, and B, their offspring has a dominant phenotype. And when I read it out like this, it becomes a bit clearer, mathematically at least, what they're asking. So if you think about it, they're actually asking us to find two distinct probabilities. The first one is the probability that any two randomly chosen organisms mate, and also the probability that their offspring has a dominant phenotype. And with probability, this word and should signal to you that you're going to actually be multiplying two individual probabilities, which are going to be A and B. And the next question then is, how do we solve the probabilities of A and B? Well, for A, I think the most convenient way to at least visualize how to do that mathematically is by actually drawing a probability tree like they've drawn for us in figure 2. So if we draw a probability tree for the sample data set that they give us, and what do they give us? They give us 2 Ks, 2 Ms, and 2 Ns. And let's say we want to know, okay, so if we were to pick at random any organism as one of the mating organisms, we'd have a chance of picking a K, an M, or an N organism. And the probability of choosing a K is 2 out of 6. Choosing an M is also 2 out of 6. And the probability of choosing an N is also 2 out of 6. Now, let's say we did pick a K as our first organism. The chances of picking a K of our second organism are what? If we had already picked this K as the first organism, then we only have one K left out of a total of 5 leftover organisms from our previous total. And this is the one thing, this is one important thing to remember throughout this problem, that repetition is not allowed here. Because we're dealing with organisms that are mating, since not, one organism can't just mate with itself, you have to eliminate that first organism from your population when choosing your subsequent mate. So in this case, there's only a 1 out of 5 chance of choosing a K as your second mating organism. But after choosing a K organism, you still have a 2 out of 5 chance of picking an M organism because we still have 2 M's left in our population. So you can see 2 M's in our little circle here. And we also still have 2 out of 5 chance of choosing an N organism. If we were to do the same thing for our M branch, we'd have something similar, but instead of having the K have a numerator of 1, here we have the M with a numerator of 1 because the first M was already taken in our first pick. Okay, and let me just draw this part. All right, I hope this all makes sense. So, in essence, you can actually think of part A also being the addition of 2 distinct probabilities, right? Because part A is asking what the probability is that 2 organisms mate. It's basically asking the same thing that you choose the first organism and the probability that you choose the second organism. So in that case, all we'd have to do is multiply the probability of choosing the first organism times the probability of choosing the second organism. So if I were to ask what the probability is of a K mating with a K organism, all I do is look at my probability tree, look for the path in my tree that contains a K and then another K, and then multiply those 2 probabilities together to find the probability that 2 K organisms mate. Now, another thing to remember, however, that's a little bit tricky is that when you have something like the possibility of mating a K and an N organism, in addition to having this branch right here, you also have this branch here, this NK. So mating a K with an N organism is going to be the same thing as mating an N with a K organism, right? Because they're the same types of organisms, and in this case, mating organism A with organism B is going to be the same as B with A. And both pairs will have the same probabilities of having a child with a dominant phenotype. However, the way to take care of that problem is, since each of these paths in the probability tree are individual events that cannot happen simultaneously, here you're asking essentially what is the probability that you choose a K and then an N to mate, or the probability that you choose an N and then a K organism to mate. So in that case, you would go down this path, multiply the probability of K and N, which is 4 out of 30, and then go down the other path, which is N and then K, and that product is also 4 out of 30. And you're asking what the probability is of choosing this path or that path, you are going to add those 2 probabilities to get the total probability of choosing an N or a K, or conversely a K or an N, to mate. All right, now that we've gone over that, so hopefully that clears up how to solve the question brought about in part A. Now we know how to use that tree diagram to find out the probability that any two organisms mate. So I'm just going to check that off because we've covered that. And now comes B. How do we find the probability that two organisms will have an offspring with a dominant phenotype? And for part B, I thought it was useful to actually draw out some Punnett squares. So remember, Punnett squares can be really useful in predicting the chance that an offspring from two individuals will have a certain phenotype based on their allele makeup. So let's say we had a gene represented by the letter G, and capital G represents a dominant allele, and lowercase g represents the recessive allele. If we were to cross that with another heterozygous parent, so let's say we have two heterozygous parents mating, which in our problem would be two M organisms mating. All we'd have to do is basically just cross the letters like so, and then the number of times each combination is represented in the square is the probability out of 4 that the child of these two organisms will have that allele makeup. So in this case, it's a 1 out of 4 chance it'll have a homozygous dominant makeup. There is a 2 out of 4 chance that their child will have a heterozygous makeup. And there's a 1 out of 4 chance of having a homozygous recessive makeup. However, while this is all true, the problem is specifically asking simply what is the chance that the child just has a dominant phenotype. And if we only care about the phenotype and not the actual alleles, we would actually add these two probabilities to get the probability of 3 out of 4, or 75%, of their child having the dominant phenotype. Because remember, even if you have a recessive allele in the heterozygous child, the dominant allele will overpower that recessive trait, and so all you would see on the outside of that child is that dominant trait. So in this case, it's just 75%. And what you would do is go back to that tree we drew, and you can actually, let's write this value, 75%, on the actual path of the tree this Punnett square represents. So we're looking for the M path that mates with another M. So here, let's put the number 0.75. Okay, and so if we were going to find the answer that our reworded question asks us, if we wanted to know what the probability is that M mates with an M and the probability that the child has the dominant phenotype, all we would do is multiply 2 by 6 by 1 by 5 to get the answer to A, and then multiply that product with 0.75, and 0.75 is the answer to B. And that total product of those three numbers is going to be the answer to the overall question of the chances of A and B happening. And so we can just do that for the rest of the branches in the tree. So I'll just kind of quickly go over each possible combination. So we can have, in addition to M and N, we can also have two homozygous dominant, and that would be 100% dominant phenotype. If we had a K and an M, that would be still still a 100% chance of the offspring having a dominant phenotype. Then let's say we wanted to find out the chances of a dominant phenotype in a K cross N. That would, again, be 100%. And what's left? Oh, and remember this K cross M is the same thing as an M cross K. So this value is valid for 2 paths in our tree. And I'll actually show you that once I get all these Punnett squares drawn out. Into M. What about K and M? That is GG. Actually, I already did that, right? No. Let's do, that's gonna be, sorry. Let's do M and N, and that's gonna be a heterozygous mate with a homozygous recessive. And that will give us a 50% chance of the dominant phenotype occurring. And if we wanted to cross an N organism with another N organism, we would have a 0% chance of them producing an offspring with the dominant phenotype. So let's go ahead and plug these numbers into our tree just to put everything in one place. So crossing a K with a K, that would be number 1. A K and an M, that is also 100%. And a K and an N, that is, should be 100% as well. But did I draw it? Yes, I did. Alright, next, M and a K, remember that's the same thing as mating a K with an M, so that's also 1. M and N, which I believe was the last Punnett square we just drew. Oh no, it's this. There's a 50% chance of their offspring having a dominant phenotype. So let's put 0.5 right there. An N and a K is the same thing as a K and an N. Oh, that got cut off. So that's just 1. NM is the same as MN. And NN was 0. Alright, so to actually answer this question, if you were to do this question by hand, all you would do is first multiply the values within the branches, and then solve for the sum of the products of each path in our tree. And by that I mean first you would go down here, multiply 2 by 6 by 1 by 1 by 5, or if you're gonna do it following the way we reworded the question, first you would find the value of A, which is the probability of 2 organisms mating. And you find that by multiplying the probability of choosing this organism times the probability of choosing then this organism. And then if you also want to find the probability of their child having a dominant phenotype, you just multiply the first probability you chose by the number 1, which is the probability that their offspring has a dominant phenotype. And then you do that for each path in this tree, and then take the sum of all of those paths, and that is the answer to this question, which asks the probability that 2 randomly selected mating organisms mate and produce a child with the dominant phenotype. Now, The next tricky part here is actually representing all this in code. So of course there are an infinite number of ways to actually write this problem in code, but I'm just going to show you my way, and it's definitely not the best way, but I think it helps you visualize actually what we just did by hand right now. So I write in Python, and I also use this Python package called NumPy. It's a pretty easy package to kind of get your hands on, at least the basics of. It's just um, a package that helps you deal with numbers, especially things like matrices, a lot easier, instead of just using embedded lists or something. Um, so this first part here, what I'm trying to do here is basically represent my dominant and recessive alleles. So recall how when we were drawing our Punnett squares, we use the letters, the capital letter to represent a dominant allele and the lowercase letter to represent a recessive allele. Here, I'm using the number 0 to represent the dominant allele and the number 1 to represent a recessive allele. And I use 0 here because just like how a dominant allele overpowers any other allele it's crossed with, when you multiply any number with any real number with 0, it could be 1, infinite, 1,000, or even another 0, you're still going to get 0. So I decided to use that property of 0 and also the properties of matrix algebra to actually represent my Punnett squares. And I'll go into more detail about that matrix algebra when we go into the actual function I made. And then these here are just a bunch of empty lists, I think, to hold some values later on in the code, but they're not super important to understand right now. And so my code is basically just one big function, define it up here, and then I call it down here, and I just plug in the values of k, m, and n in there. And the first part of my code is basically the part of the code that answers my question in part A of our rephrased question, which is what is the probability that any two randomly chosen organisms mate? And you can see here, I go through each possible combination of mating organisms by doing this nested for loop. And then I cover the condition of the probability of an organism mating with an organism of a different type. And then I also cover the probability of an organism mating with an organism of the same type by ensuring that that second numerator is an n-1. So that's right here. All right, and then I just append this empty list that I created above the function to hold all my values. And I tell my code to just print each probability so I could see the numbers as the code runs. And then I also sum up each the probabilities I have in that list I've made. And if I've done everything right, my sum should be equal to 0, right? Because if I sum the probability of every possible scenario occurring, then I should get 100%, because that should cover 100% of all the possible scenarios. So if I go to the code that I ran, let me move that. So this right here is the first print statement, which is the list of my probabilities. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 numbers, and that makes sense because I have 9 paths in my probability tree, right? And then this is the sum of all of the numbers up there. It's 0.999. It should be 1, but I think that's just like a Python rounding error thing. But yeah, it's essentially 100%. And then next, I have in my code this chunk, which is basically part B in my rephrased question. And here, I also use a nested for loop, but I use it for those matrices that I defined in the beginning those matrices represented by zeros and ones to kind of represent my Punnett square crossing. So here I use a bit of matrix algebra and I transform my first matrix by the matrix it's being crossed with. And then that results in a 2 by 2 matrix. And I then count the number of zeros in that 2 by 2 matrix and divide it by 4 to get the probability that the offspring of those two crossed parents will produce a child with a dominant phenotype. And to actually show you mathematically what's going on, basically what that's doing is I am taking something that looks like this, multiplying it by this, and if I cross matrices of these dimensions together, then I should get a matrix of this dimension, and it's actually going to have 4 zeros in it, and this line right here just calculates the number of zeros that appear in that 2 by 2 matrix and divides it by 4. All right, and then I also add each of those numbers to an empty list that I think I made in the beginning. Yep. And then I print it just to be able to see what's happening in my, what did I just do? All right, I hope I didn't just screw it up. Okay, and then I just print it again and I get these numbers. And again, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, which again makes sense because I have 9 numbers in this list and of course 9 paths in my probability tree. And finally, I have this. What did I do? I don't think I need that. Yeah, sorry, I must have clicked something and like copy and pasted something by accident before. All right, so here, what I'm doing is taking each number in each of the 2 lists I created and multiplying each number by its corresponding number in the other list. So basically, I'm multiplying A times B. And then in the end, I sum all those numbers up to get my probability of choosing A, 2 organisms from our total population, and B, the probability that their children are of the dominant phenotype. So when I plug that into my code, I get this number right here, which was 0.78333. And all right, so I must have moved something around in my code when I was explaining it. Oh, I just completely copied and pasted it again. Let's see if this works. All right, there, sorry. Oof, okay. So I just ran it again just to make sure that code is correct. And after I deleted what I accidentally copied and pasted in there while I was clicking, I get the same numbers, it looks like. Oh, but it looks like I forgot to print a list, whatever. And this is my final answer, 0.78333. And if we go back to the sample output, it's also 0.78333. So we can be confident that our answer or that our code works. And I also tried it with the data set that they gave me, and eventually I got it right. So I hope this helped a bit in first understanding what the problem is actually asking you mathematically, and also gives you an idea of how to like start writing the code. I definitely recommend not using my code as it is. Like, definitely try making your own code, especially for this problem. I think it's pretty fun to try to think of a way to do it through Python or any other language. And Let me know if something I explained was not clear or if I just forgot to explain something completely. And let me know how this video worked for you and if it was helpful. All right, so thanks for watching.